So, in the last class we have seen how to remove the useless symbols from a context free grammar. We have also seen how to remove the epsilon productions from a context free grammar. But if the language contains epsilon, you must have a rule of the form s goes to epsilon, and you must make sure that s does not appear on the right hand side of any production. The next result we will see is that we can remove the unit productions also. What is a unit production? A unit production is of the form A goes to B, a non-terminal going into B, another non-terminal. Such a production is called a unit production. So, you may want to get rid of these rules. As I mentioned, if you introduce too many of this unit production in a compiler, if you want to represent a programming language by a grammar and use a compiler for that, then if you have too many of this unit production, the compile time will be more. So, you want to avoid these unit productions. So, how to remove these unit productions? First of all, you must see from which non-terminals find all pairs A, B such that A, from A you can go to B, need not be in one step, but in many steps. Okay. That is, you are starting with the grammar G is equal to NTPS, and in this grammar you want to remove the unit production without affecting the language generated. Now, you split P into two sets, P1 union P2, where P1 is a set of unit productions and P2 is the other set, non-unit. Now, you construct an equivalent grammar G dash is equal to NT P dash, same non-terminals, same terminals, but the production rules are different. What is P dash? P dash consists of all P2, all P1 will be removed, but instead you will add some more rules. And what are these rules you are going to add? Now, for every pair AB, for every pair AB such that from A you can go to B by unit productions. It may not be in one step. If A goes to B is a unit production, you can go in one step. Or if you have A goes to C, C goes to B, then you will go to B from A in two steps. So, for every pair such that A goes to B, add rules A goes to beta if B goes to beta belongs to P2. If you have a rule B goes to beta in P2, then you add the rule A goes to beta to this. So, P dash consists of P2 plus all such rules added, all such rules added. Okay. Then you can show that LG is equal to LG dash. Again, a formal proof on the number of steps and so can be given, induction on the number of steps, but informally you can see like this. We can see that suppose you have a step from which you derive B, and in a derivation from S you may have a sentential form, say alpha A gamma, somewhere you get gamma. Then after some steps making use of unit productions only, you get alpha B because from A you are able to derive B, and these steps are using only unit productions. These steps use only unit production. Then after some step you may be using some rule B goes to beta I. So, after the next step may be alpha, beta I, gamma, then etc. But in the grammar G dash which we have constructed, you have added the rule A goes to beta I, you have added the rule this. So, instead of going through all these steps, start in, this is happening in G, and in G dash what will happen is you are getting alpha A gamma, and instead of applying these unit productions and then applying B goes to beta I, you straight away apply A goes to beta I. So, alpha beta I gamma you get in one step. Then the derivation in G dash can proceed. So, the effect is the same. Instead of applying A derives B and then B derives beta I, straight away you are using the rule A goes to beta I and deriving this in one step. Okay. So, by removing the unit productions and adding the rules of the form A goes to beta, the resultant language is not changed, the language generated is the same. So, it is advantageous to do this rather than use the unit productions, but one thing you must be careful, the number of rules here will be enormously increased, depends on, suppose I have such pairs A B 5, 6 or 7 pairs like that, the number of rules is going to increase very much, but if I have just one pair you can just remove it and so on. So, the number of rules in P dash will be much more than the number of rules in P. And when you use a parser to reduce a string, at every point you may be able, you may have to check which rule can be used for reduction. Then if the number of rules is too much, every rule you must try. So, that lookup procedure will be more, it may take more time. So, you have to see that there is a balance, that while removing the unit production you are not adding too many of other rules. But anyway, this result tells you that you can get rid of unit productions, it is not necessary to use the unit productions. Let us take an example. A simple example let me take. S goes to ASB, S goes to A goes to CAD, A goes to CD. If I have this grammar, what is the language generated? The language generated is, first you will use this rule many times, then from S you go to A, then use this to generate equal number of C's and D's. So, it will be A power n, C power m, D power m, B power n, m greater than or equal to 1, but n can be 0 also. Okay. This will be the language generated, and there is a unit production. Now, we want to get rid of this unit production. So, by this procedure you split it into P1 and P2. P2 will consist of these 3 rules, P1 will consist of this. So, remove this, you have to remove this, but P2 you have to keep as it is. So, these 3 rules you keep. Then you have a pair SA, right. Then whenever there is a pair SA, the right hand side you replace with the right hand side for every rule with A on the left hand side. So, what are the rules you will be adding now? The rules you will be adding will be S goes to CAD, S goes to CD. So, instead of applying S goes to A, then A goes to CAD, you can straight away apply this rule. Instead of applying S goes to A goes to CD, you can straight away use this rule. Now, look at the grammar without this rule, but adding to these 2 rules. You will see that any number of equal number of A's and B's can be generated using this rule. Then you can go from S to this or S to this. You see that at least one C and one D must be generated. Use this many times, then use this, one CD will be generated. Use this many times, as many times you want, and then use this once, and then this you will get C squared D squared. If you want to get more, use this many times for A power n, B power n, then C cubed D cubed if you want, use this once, use this once, use this once. Then any number of C power m, B power m you can D power m you can generate with proper combination of these 3 rules. Just one CD alone you want means you use this rule after applying this rule. Okay, you need not have to apply this rule at all, because n can be 0 also, just CD also belongs to the language. You can start with S and derive CD. There n can take the value 0, 1, 2 etc. M takes the value 1, 2, 3, there should be at least one C and one D. Okay. So, this is the way you get rid of the unit productions. So, we have seen how to remove the useless symbols, that is, from every symbol should occur in a derivation like every symbol x must occur in a derivation like this. From S you should be able to reach x, and then from x you should be able to derive a terminal string. So, for that we have seen that how to apply 2 lemmas, lemma 1 and lemma 2, and you have to apply them in that particular order. The first one, make sure that for from every non-terminal a terminal string is derivable. The second one, make sure that every symbol is reachable from S. So, now you have this result, every CFL without epsilon can be generated by a CFG without epsilon productions, unit productions and useless symbols. So, in which order you go about? Because we are without loss of generality, we are assuming that the language does not contain epsilon. So, the first step will be remove the epsilon productions, because when you remove the epsilon productions, you may introduce unit productions. So, first remove the epsilon productions, after removing them remove the unit productions, then after doing this remove the useless symbols, use lemma 1 and lemma 2 in that order. So, ultimately you will end up with a grammar which does not have epsilon productions, unit productions and useless symbols. Such a grammar is called a reduced grammar. So, we are interested in finding out the reduced grammar for a language. Now, one assumption we have made is that it does not have epsilon. So, we have assumed epsilon does not belong to L, the language with which we started. Suppose, what do we do? Suppose epsilon belongs to L, then how do we go about it? In this case, L minus epsilon can be generated by a reduced grammar. L minus epsilon will be reduced by a grammar. Now you have to include epsilon. For that, what do you do? So this is, suppose this is generated by G is equal to NTPS. Then you have G dash, where you add one more symbol S1, same terminals, P union, say P1 I will put, comma S, the new symbol will be the start symbol. You add one more symbol S1 to the set of non-terminals and make it the start symbol. Okay. And all these productions will be there, but you may add a few more productions. And what is the set of productions P1 you are going to add? First of all, you want to include epsilon, isn't it? You want to include epsilon in the language. So you have a rule S1 goes to epsilon. So if you want to derive epsilon, you will use this rule alone, S1 goes to epsilon, and then derive epsilon. No other steps involved. Okay. Other rules will not have epsilon on the right hand side. But starting from S1, you also have, if S goes to alpha belongs to P, add S1 goes to alpha to P1. If S goes to alpha belongs to P, the earlier start symbol going into alpha, then you also add S1 goes to alpha. Okay. So P1 will consist of rules of the form S1 goes to epsilon and S1 goes to alpha, where S goes to alpha belongs to P. Okay. This makes sure that the start symbol does not occur on the right hand side. Now alpha cannot contain, alpha belongs to P, the earlier grammar did not have S1. So alpha cannot contain S1, right. So S1 will not occur on the right hand side of any production. And if you want to derive epsilon, you have to use this rule and this rule only, and you will be able to derive epsilon. Okay. Now if you have a derivation in G of the form S goes to some alpha then something etc. In G dash you will have S dash goes to alpha, I am sorry, S1 goes to alpha, same derivation you can have, the first step alone will be changed. So whenever a string is derivable here, it is derivable here, and whenever a string is derivable here, it is derivable here. Apart from that, you are also deriving epsilon. Okay. So L minus epsilon is generated by a reduced grammar, L is generated by G dash, and in G dash you have the property that the start symbol does not occur on the RHS of any production. The reason for this is if you have a derivation S1 goes to this some alpha, alpha 1, alpha 2, whatever it is. If you have a derivation, the successive sentential forms will be non-decreasing in length. Length of alpha 1 will be more or equal to alpha, length of alpha 2 will be more or equal to alpha, and so on. It will not decrease. But if you have S1 on the right hand side, the start symbol, because of this rule, anytime you will be able to apply this rule, the successive sentential form can reduce in length. You want to avoid that. In any way derivation, you want to make sure that the successive sentential forms are non-decreasing in length, and that is why you want to avoid having S1 on the right hand side of any production. Since you are adding this rule, S1 goes to epsilon. That is the reason. Okay. So, whenever we have this problem with epsilon, epsilon has slight, whenever you want to have the empty word, there will, in the proofs and all, there will be slight problem. So, you want to avoid writing a very lengthy proof. So, you make sure that the grammar generated has this format. Okay. So, the next thing is we shall study two normal forms. What are the normal forms? One is called the Chomsky normal form. It says that every CFL without epsilon can be generated by a CFG with rules of the form A goes to BC or A goes to A, where A, B, C are non-terminals and A is a terminal. So, without loss of generality, we can assume that the language does not contain epsilon, and we know how to accommodate for epsilon now. So, if a CFL without epsilon, then it can be generated by the grammar with rules of the form A goes to BC and A goes to A. That is, on the left hand side, as usual, for any CFG you have only a single non-terminal. On the right hand side, you have two non-terminals or a single terminal. On the right hand side, you can just have two non-terminals or a single terminal. So, every CFG you can bring it to this form. This is called Chomsky normal form. How can you bring it? Let us take an example. By considering an example, it is much more easy. Let us take the grammar. This, you know that the language generated is a power n, b power n, n greater than or equal to 1. Now, we want to bring this to Chomsky normal form. How do we go about doing this? First step will be, for every terminal symbol, introduce a new non-terminal. So, for small a introduce a non-terminal, I should not, for small a you use a and small b use capital B. Now, the rules will become, in this example the rules will become S goes to A S B, S goes to A B, A goes to A, B goes to B. Now, you can see that this rule is in Chomsky normal form, this rule is also in Chomsky normal form, this rule is also in Chomsky normal form, but this is not in Chomsky normal form. So, you have to do something about it. So, the second step is, if A goes to B1, B2, Bm is a rule. Note that now you have made all the symbols on the right hand side as non-terminals. So, B1, B2, Bm are all non-terminals now. So, this rule you can split like this, A1 goes to B1, D1, D1 goes to B2, D2, like that up to Dn minus 2 goes to Bn minus 1 Bn. The previous one will be Dn minus 3 goes to Bn minus 2 Dn minus 2. So, at the end of the first step, after you have replaced every terminal with a non-terminal, the rules will be either in this form, Chomsky normal form terminal rules, or rules will be of the form on the left hand side you have a non-terminal and the right hand side you have a string of non-terminals. So, when you have this, when you have a string of non-terminals on the right hand side, you want to have only 2 of them. So, you have to split this rule by introducing new non-terminals D1, D2, D3 etc. up to Dn minus 2 and split this rule. But you must be careful that if you have 2 such rules, when you want to split these rules, you are introducing the non-terminals D1, D2 etc. Another rule is there, then you must introduce some other non-terminal E1, E2 etc. You should not use the same non-terminals there, because they will mix up and then create problem. So, in this example which we have considered, these 2 are in Chomsky normal form, this is no problem, it is in Chomsky normal form. The first rule alone is not in Chomsky normal form. So, you introduce a new non-terminal, say D, S goes to D and then D goes to SB. You introduce a new non-terminal and have S goes to AD and D goes to SB. So, instead of applying like this, the same result will be achieved in 2 steps by applying AD first and then D goes to SB. When you apply, it will be AS. So, without any problem, any grammar you can convert into Chomsky normal form. Let us take one more example. S goes to ASA, S goes to BSB, S goes to C. What is the language generated? The language generated consists of strings of the form WCWR, where W belongs to AB star, any string of A's and B's. Now convert this into Chomsky normal form. Convert this grammar into shortened form is CNF, Chomsky normal form. The first step is introduce a new non-terminal for every terminal symbol. If you do that, you will get S goes to ASA, S goes to BSB, S goes to C, A goes to A, B goes to B. These are in Chomsky normal form, no problem. So, the other two rules you have to convert into Chomsky normal form. So, when you want to convert this, what do? You introduce a new non-terminal, and instead of this you will have S goes to say AD, introduce a new non-terminal D and have it as S goes to AD, D goes to SA. Now, when you want to convert this rule, introduce another non-terminal E, not the same, you should not use the same D. S goes to BE, E goes to SB. So, the effect of applying this rule is achieved in two steps by applying this first and then this. The effect of applying this rule is achieved by applying this and this. Now, all these four rules are in Chomsky normal form. So, every CFG can be converted into Chomsky normal form. There is another normal form called Greiba normal form. There are several normal forms for CFG, but these are the two which are mainly used. The Chomsky normal form is very useful in proving some results about context free grammars. Greiba normal form is useful for proving the equivalence between push down automata and context free grammars, and also sometimes in parsing purposes. If the grammar is in Greiba normal form, it is easy to parse. What is Greiba normal form? Every CFL without epsilon can be generated by a CFG with rules of the form A goes to A, B1, B2, Bm, A goes to A, where A, B1 etc. are non-terminals and A is a terminal. That is, on the left hand side you have a single non-terminal, on the right hand side you have a single terminal or a single terminal followed by a string of non-terminals. You may have one non-terminal, two non-terminals, three non-terminals, any number you can have. So, the rules are of the form such that on the left hand side you have a single non-terminal, on the right hand side you can have a single terminal or a single terminal followed by a string of non-terminals. So, you can bring any CFG to this form. Let us see how we can do that. Again take the same simple examples. S goes to ASB, S goes to AB, this we have already considered. The first step is for every terminal symbol introduce a new non-terminal symbol. So, let me illustrate after every step how for this example. There are 5 steps in the conversion, but this example may not use all the 5 steps. So, let me see how we can do this. So, S goes to ASB, S goes to AB, then you have A goes to A. This step is the same as the previous conversion to Chomsky normal form. Now, you find that because of this the language generated is not affected, the language generated is still going to be the same. First you will generate capital A power n, B power n and convert all this capital A's to small a's and capital B's to small b's. Now, these two are already in Greibach normal form. The second step here will be introduce an order among non-terminals by renaming them. So, the grammar which we considered earlier, you can call them as A1, A2, A3. So, make S as A1, A as A2, B as A3. There are 3 non-terminals here. So, make S as A1, A as A2, B as A3. You are renaming them. So, now the rules will become A1 goes to A2, A1, A3, A1 goes to A2, A3, A2 goes to A, A3 goes to B. So, you are having an order among the non-terminals. This is also very simple, it is just the language generator will not be affected because just you are renaming the non-terminals and calling them as A1, A2, A3. The third step involves the use of 2 lemmas. We will see what are the 2 lemmas now. Lemma 1 is this: define an A production to be a production with variable A on the left. An A production is a production with variable A on the left. Let G is equal to NTPS be a CFG, then there is an A production, A goes to alpha 1, B alpha 2. For some reason you want to get rid of this rule. Okay. Now, when you want to get rid of this rule, what should you do? Be a production in P and with B on the left, here B is a non-terminal, with B on the left hand side you have a set of production, B goes to beta 1, B goes to beta 2, B goes to beta r. A set of productions you have with B on the left hand side. With B goes to beta 1, beta 2, beta r, B the set of B productions. Then from G you construct G1 such that G1 has the same non-terminals, same terminals, but the productions are same. Let G1 be obtained from G by deleting the production alpha 1 B alpha 2. For some reason you want to get rid of, we will see why we need this lemma later. So, you delete this rule, but when you delete this rule the effect must be obtained by some other rules. So, when you delete this rule what you do is you add the rules A goes to alpha 1 beta 1 alpha 2 alpha 1 beta 2 alpha 2 alpha 1 beta r alpha 2. So, R rules you add, then the language generated does not change. So, in essence what happens is in this grammar I have a derivation, somewhere I have alpha A beta, probably alpha A gamma I can read. And the next step I use the rule alpha 1 A goes to alpha B beta, I use this rule. So, A goes to alpha B beta I apply and the next gamma will be there and the next step beta will be replaced by some beta I, alpha 1 alpha beta I beta gamma. Then the derivation proceeds. Now, this rule you want to remove. Now, when you remove this you are adding the rules of the form A goes to alpha beta 1 beta, A goes to alpha beta 2 beta and so on, A goes to alpha beta r beta, such rules you are adding. So, at this stage instead of using this rule and then replacing B by beta I, straight away you can use the rule A goes to alpha beta I beta and write it as alpha 1 alpha beta I beta gamma. In the original grammar G, you may have a derivation in which A is replaced by alpha B beta first and then B is replaced by beta I. But in the new grammar G dash you do not have this production A goes to alpha B beta. So, but instead you have added these productions. So, instead of getting it in two steps like this, straight away you apply the rule A goes to alpha beta I beta and get this. Then the derivation will proceed as before. So, the effect is the same. So, the language generated will not be affected. This is when you want to get rid of a particular rule for some reason. Then there is another lemma, this also we will be making use in steps 3 and 4 of that conversion to Greibach normal form. So, let us see what is that. let G is equal to NTPS be a CFG, and then this is the context free grammar. Then let A goes to A alpha 1, A alpha 2, A alpha R be the set of A productions for which A is the leftmost symbol of the right hand side. Such rules are called left recursive rules. A rule of the form some A going to alpha A beta is called a recursive rule. A rule of the form A goes to A alpha, where A is the first symbol, leftmost symbol, this is called a left recursive rule. A rule of the form A goes to alpha A, where A is the rightmost symbol, that is called a right recursive rule. In many cases, you may want to avoid left recursion. When we learn about parsing, we will see that sometimes we will want to avoid left recursion. But when you want to avoid left recursion, you will be introducing right recursion. But that is okay. So, that is what we are going to do here. We want to avoid the left recursive rules. We do not want to have left recursion. Then let us see what. Let A goes to A alpha 1, A alpha 2, A alpha be the set of A productions for which A is the leftmost symbol of the right hand side. Then there are other rules. A goes to beta 1, A goes to beta 2, A goes to beta S be the remaining A productions. They are not left recursive rules. Then you want to replace all the A rules by a set like this. You have a new grammar where you introduce a new non-terminal Z, and instead of having the set of A productions, so the new grammar, let G1 be equal to N union Z T P1S be the CFG formed by adding the variable Z to N and replacing all the A productions by the productions A goes to beta I, A goes to beta I Z, where I varies from 1 to S, and Z goes to alpha I, Z goes to alpha I Z, where I varies from 1 to R. So, earlier with A you have R left recursive rules and S other rules which are not left recursive. But when you want to replace, you are introducing a new non-terminal Z and you are having 2S rules like this and 2R rules like this. So, actually what you are trying to do is the R plus S rules you are replacing with 2R plus 2S rules. Now, how do we justify this? So, you are having A goes to A alpha 1, A alpha 2, A alpha R rules which are left recursive, and A goes to beta 1, beta 2, beta S. S other rules. So, R plus S rules you are having. Now, suppose you are applying starting from some A, then you have A alpha 1 and from this you are deriving something. I would put A alpha I1. So, one of the rules I am applying here. Then from this again another left recursive rule I am applying, A alpha I2, and from this you may derive something. Then again from this you have A alpha I3, and from this you may derive something. You can proceed like this until you have A alpha I n, and then here you use the rule a non-recursive rule beta j. From this again you can derive something. So, from this A, the string derived is beta j alpha I n minus 1 alpha I 1. The string derived is this. Okay. Now, the same string you must be able to derive with the replaced rules. What are the rules which you have replaced? A goes to beta I, beta I j, I can put A goes to I z, where I varies from 1 to s, then z goes to alpha I, z goes to alpha I z, where I varies from 1 to r. Now, how do I get the same effect with these rules? Start from A, then use the rule beta j z. Then you use the rule alpha I n z, you have such a rule. From this again you can derive something. Then from this alpha I n minus 1 z, then again use the rule alpha I n minus 2 z and so on, until you have z goes to alpha I 2 z, then z will go to alpha I 1. So, the string generated here will be beta j alpha I n minus 1 etcetera up to alpha I 1, and from this alpha is again something else can be derived. So, the string generated is beta j alpha I n minus 1 alpha I 1. Here you have the same effect by using this rule first. A goes to beta j z, so beta j is generated, then you can use the rule of the form z goes to alpha I n z, then z goes to alpha I n minus 1 z and so on. So, you will get the same string beta j alpha I n etc. So, the effect of using such rules you can obtain from this also. So, the language generated does not change, it remains the same, but instead of r plus s rules, now we have 2r plus 2s rules. And what have we achieved by doing this? We have avoided left recursion. Left recursion is avoided, but what have we done for that? We have introduced right recursion. Z occurring as the last symbol introduces right recursion. Okay. So, these two lemmas we have to use again and again in the step 3 and 4 of the conversion to Gray-Bag normal form. There are 5 steps there. We shall consider the examples and the procedure, continue with that in the next class. These are not the only 2 normal forms, there are other normal forms as well, but these are the main normal forms which are used. Especially Gray-Bag normal form is essential in proving the equivalence between push down automata and context free grammars.